Our project is on the effects of heat treatment, bend diameter, and wire thickness on bend angle. Our names are Hugo, Ethan, Kathy, and Binni. This is our agenda. The design of experiment is the two-level design for three factors, which are common quantitative inputs in metal fabrication. The factors are bend radius, wire thickness, and preheat treatment over a gas stove, all with two different values representing the low or high levels. We have 4 replicas of each unique run for a total of 32 measurements. The goal is to determine the effective factors on the final bend angle of a wire.
For our fabrication method, we chose to design a jig to control the bend radius and ensure a consistent method of bending for each sample. The jig ensured that the force would be applied to the wire at the same location for all samples and that all samples would be bent to the same set angle of 45 degrees. We made use of a swappable insert to change between our two bend radii of 2.5 mm and 5 mm in order to use the same jig to create all the samples. To produce the sample, we first load a wire of 70 mm into the jig. We then secure the wire using a press. We then load the dowel behind the wire and pull the dowel until the wire makes contact with the insert and hold for 4 seconds. Finally, we uninstall the press, remove the dowel, and extract the sample from the jig.
Measurement technique. The comprehensive set of samples that are obtained are captured using iPhone. These images are saved as PNG files and uploaded to ImageJ and image processing software. Now, the software has built-in tool for measuring the angle between the segment and line selection. The angle is defined by 3 points, 2 points at each end of the sample and the third point directly in the middle of each side of the bend. The command M records the angle in the result window measured up to 3 significant figures.
The computed factor effects from the main effects plots of each input factor shows that increasing the bend radius from 2.5 to 5 mm will increase the angle by 7.481 degrees. Increasing wire thickness from 0.54 to 0.64 mm will decrease the angle by 8.926 degrees. And heat treatment is the most significant factor because preheating from 0 to 5 seconds will decrease the angle by 26.12 degrees. The slopes of the interaction plots shows that the most significant two-factor interaction is between the wire thickness and the bend radius, while the last two interaction plots shows no interaction between its two factors.
For the analysis of variance, we calculate the sum of squares for each interaction and the degrees of freedom to find the mean squares. Using the mean squares, we can then find the f-statistic and calculate the p-value using the f-statistic and degrees of freedom. We can also find the f-critical value using an f-critical value table and the degrees of freedom. We can then determine if any of the interactions are significant for the chosen significance level alpha. We can either compare the p-value to alpha, where the p-values above the alpha value are considered significant, or compare the f-statistic to the f-critical value pulled from f-critical value table based on the chosen alpha, where the f-statistics greater than the f-critical values are considered significant. For our analysis of variance, we chose an alpha value of 0.05. This would mean that the most significant single interaction is C, heat treatment, and the most significant of the multiple weight interaction is ABC involving all three factors. The least significant single interaction is A, wire thickness, and none of the other multiple weight interactions are considered significant at the chosen alpha value.
Regression modeling. The statistical correlation of criteria and predictor variables are characterized through a regression model. The response model equation obtained delineates the heat treatment, bend radius, and the three-factor interaction have explicit impact on the final angle of bend. Now, the response surface model plotted for two significant factors with output renders the impact to be linear. The empirical relation states the angle of bend increases by 7.789 with per unit increase of bend radius and mm increases by 16.552 times with increase of preheating time in seconds.
Residual analysis shows us the quality of our sample data. On the left, the normal probability plot shows that our sample data are fairly normal, with no significant outliers. On the right, the residual plot shows us that there's no abnormal dispersion in our sample groups. Some have smaller dispersion than others, but overall, no abnormality is observed in the residual plot.
Conclusion. The DOE for analyzing effect of wire thickness, bend radius, and preheat treatment on final bend angle that includes a set of angle of 45 and spring back based on 2 levels, 8 runs, and 4 replicates concludes preheat treatment has most significant one and wire thickness the least. Our data analysis has statistically proven our result. Using ANOVA, on comparison with F critical of 4.15, the F statistical value for factor C is 282 and factor B is 23.1. Since these values are greater than F critical, it possesses significance. The slope of factor effect plot of preheat and regression model equation supplements our result.
Here are the references used for our project. Thank you for listening to our presentation.